Welcome to our video on the slope of the tangent line and how to find it algebraically. Before we get started, let me set up a little bit what you're seeing in this first image, and then I'm going to have you go watch the video that's posted on Google Classroom labeled secant line. And you'll just watch some of that video, and then you'll come back and finish this notes video. So let me explain first what this image is that you're looking at, because this is what she's going to use in the video. So we have set up a graph, some random graph we're going to call f of x, this black line here. And what we've done is we've graphed a secant line. Okay, so that secant line, definition of a secant line is just that it intersects a function in 2 points. So we have graphed this secant line. So we're going to call one of the points x comma f of x. And then the other point, we're going to add h to our x value. So we're essentially saying move h units to the right, okay? And then we're going to have to then account for that in our function as well. So our y value will be whatever f of x plus h is. This distance is the distance between f of x plus h and f of x, because that's our y values. This distance is the distance between x plus h and x, which just ends up being h. The secant line we're looking at, we're trying to find the slope of that. Now we're going to write down the slope of that here in a second, and then I'm going to have you go watch the video, the other video. So when we talk about slope, we talk about the change in y over the change in x. So looking at our figure, if we wanted to write the slope of that pink line, we would take, using our slope triangle, the change in y, and I'll go ahead and write this out what we're doing. So change in y over change in x, and what that ends up being, the change in y is this value here. So it's f of x plus h minus f of x. The change in x just ends up being h. Now this should look familiar. This is the slope of that pink line. It looks a lot like what we've been talking about before. Now what I want you to do is pause this video, go watch the video that's linked on Google Classroom called secant line, and then come back and we'll continue talking about where this is going to go. So if you watched the video, what she showed in her animation was that the closer you put these 2 points together, so the closer this point moves to the original point, the shorter or the smaller these differences get. Okay, and they continue to shrink until eventually we have an overlapping point, and h just becomes 0. That distance that we traveled on the x-axis to get the second point becomes 0. And what we end up with when those 2 points overlap and h becomes 0 is what we call the tangent line. So as h, the distance between those two coordinates, becomes closer and closer to 0, the secant line approaches what we would call the tangent line. This gives us a way to find the exact slope of the tangent line at some point. So the definition of the slope of a graph. So we're going to say that the slope, or m, of the graph of f of x at a particular point is equal to the slope of the tangent line at that particular point. So we find that by looking at the limit as h approaches 0 of the secant line slope. And that was the very first picture we looked at in these notes. And that just becomes what we've been talking about. This all becomes our difference quotient. So what we're really saying is that that difference quotient gives us the slope of the tangent line at a particular point that we will just call x comma f of x. Now this is true only if the limit exists. So there will be times when our limit won't exist and then we won't have a slope of the tangent line. So let's go ahead and just practice with this. We've already been using the difference quotient, and this is identical to the difference quotient. We're just calling it, we're giving it a name now. Other than just calling it the difference quotient, we're saying what is this actually finding for us. So for example 3, and I'm not sure, I don't know if it's example 3 or example 1, but it doesn't matter. We want to find the slope of a line tangent to our function, f of x equals negative 2x plus 4, and that's all we're going to do. We're going to find the slope of a line tangent to that that particular function. Now what we're going to be finding here is the slope at any point. Okay, so we're going to be saying this is the slope for any point that's any tangent line on that graph. Okay, so we're going to use our difference quotient just like we have been. So we'll say the limit as h approaches 0. And I won't go through all of the development of f of x plus h and that kind of thing. I think by now you should be able to do that. We would have -2 times x plus h plus 4 minus, and then -2x plus 4 all over h. Little bit of algebra here, right? We'll have -2x minus 2h plus 4 plus, 2x minus 4 all over h. And then what we end up with here, when our x's are going to become 0, and then 4 minus 4 is also 0, is just -2h over h, which we can reduce to -2. So that limit is -2. So we know that no matter what point we choose, the slope of a line tangent to that graph anywhere is going to just always be -2. And that makes sense because we said that a line has a consistent slope, right? Its slope is unchanged anywhere on that graph. So it should be that we get a specific value for the slope of any tangent line to that graph. Now, what happens if our function is a little more interesting? So this time, first I'm going to find the slope of the tangent line to any point on that graph, and then I'm going to actually get a little more specific. I'm going to say what happens if I want to know the slope of the tangent line at that particular point. So just to give you an idea of what we're really doing here. So let's imagine that we have the graph y equals x squared, okay? And I'm just going to make a really quick sketch of that graph, just getting us enough points so we can actually talk about what's happening here. We have this function. Here's our graph, f of x equals x squared. What we're doing is we're saying go to the point -2, 4, which is right here. Find the slope of that tangent line. Now, up till now, we had to rely on being able to draw the line, the tangent line, as best we could, and then estimate the slope. But what we're going to do now is find the exact slope of that tangent line. And to do so, we're going to use the difference quotient. So I am going to take my function, f of x equals x squared, and I'm going to use my definition of the slope of the tangent line. So the limit as h approaches 0 of f of x plus h, so that's x plus h squared, minus f of x, so minus x squared, all over h. Little bit of algebra here. And we'll have x squared plus 2xh plus h squared minus x squared. And I'm not really taking my time through this process because by now we've done a lot of these. We simplify that expression. We get 2xh plus h squared over h. I can factor out my h. And I have a giant 1. So then I get the limit as h approaches 0 of 2x plus h. Now is the point in this process when I can plug in 0 for h, right? So then I'm going to get that my limit is 2x plus 0, or 2x. Now, what this tells me is that anywhere on the graph, no matter what point I pick, I can use this to find the slope. So this guy is the slope of the tangent line. At any point on f of x equals x squared, okay? So no matter what point I pick, I can find the slope of the tangent line. Now, I gave a specific point, the point -2, 4. So here's how we're going to use that. So we have the slope is given by the function 2x. Well, in order to find the slope at the point -2, 4, I can take my x value and plug it into my formula for slope. So I would have to take my slope at -2, 4 will be found by doing 2 times -2, and that ends up being -4. So the slope at -2, 4 is just -4 over 1. And if we look back at our graph, it was just a rough sketch, but it is definitely going to be a negative slope, and it looks pretty steep. So we're probably on the right track with that with that particular question. Now, just to play this out a little bit longer, what if I said, now find the slope at the point 1, 1? So if I wanted you to find the slope at the point 1, 1. So if I wanted to do that, I would plug in 1 for x. Okay, now we look at our slope. It's more shallow. Okay, that definitely makes sense. It's less steep and it's a positive slope. So we are able to find the exact slope at that point. So what we are doing is it actually has a really special name. So this whole process is called finding the derivative of a function. So the derivative is written a bunch of different ways, okay? So it could be written as, we call this f prime of x. You could also just call it the derivative of f of x. Sometimes you'll see it written as dy over dx, okay? It's just the derivative. There's other ways of writing it. Those are going to be probably the two that you're going to see the most often. You may even see it sometimes written as y prime. You could see it as, d over dx of f of x. There's lots of different ways to see the notation for this. We are going to stick to this one. So I'm either going to say f prime of x or the derivative of f of x. Either one of those mean the same thing. And I do have the space here for other notations for the derivative. I've already kind of written that out. So this whole kind of development over the last 3 lessons has been to get to this definition. So the derivative of a function is given by finding the limit as h approaches 0 of f of x plus h minus f of x all over h. It has a special name, and this is what you will start with when you get to calculus. Probably your first unit one of the first units is going to be starting to look at the derivative and looking at different shortcuts and different formulas and different ways to find the derivative. So because I know we always need more practice when it comes to radical functions, I want to do one more with you for practice, and then I'll let you we'll end the video there. So we're going to find f prime for f of x. We're going to find the derivative of f of x when f of x is equal to the square root of x. So to do that, to find the derivative, we're going to use our limit. So the limit as h approaches 0 of that function is going to be found by doing the square root of x plus h minus the square root of x all over h. Now, we find the limit of this by, remember our strategy is to multiply by something that will create a difference of squares, otherwise known as the conjugate. We'll multiply numerator and denominator by that. Like I said, this is the one that everybody needs more practice with, so we'll do this one. We end up with the limit as h approaches 0. Some algebra in the numerator. Remember, this is a difference of squares, so we end up having those middle terms be 0. So we just multiply the first and last terms in each set of parentheses. We get x plus h minus x all over h times the square root of x plus h plus the square root of x. Simplifying our numerator, we just get, whoops, I forgot limit. We just get h in the numerator, so h over h times the square root of x plus h plus the square root of x. There's our giant 1. And we get the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now we've gotten rid of that problem in our denominator where we had something that was going to give us 0 if we plugged in h. So now we can just plug in 0 if we plugged in 0. So now we can go ahead and plug in 0 for h, and we get the limit as h approaches, I'm sorry, we're not going to get the limit anymore, we're finding the limit. We get 1 over, it's a little loud in the hallway, sorry about that, the square root of x plus 0 plus the square root of x, which we can simplify to be 1 over 2 square root of x. So this, remember, is the slope of the tangent line at any point on f of x. We're given a couple of very specific points. So I'm going to write that down here below. What we found is the slope at any point is given by 1 over 2 square root of x. So let's say I want to find the slope at point 1, 1, okay? So the slope at the point 1, 1. Well, I'm going to have to take my slope at any point, which is 1 over 2 radical x, and I know that x is equal to 1, so I'm going to plug that in. And I get 1 over 2 times the square root of 1, which just ends up being 1/2. So the slope at 1, 1 is just 1/2. Now, what if I wanted to find the slope at 4, 2? Again, this is my x value, so I take my original function, whoops, kind of a sloppy one there, 1 over 2 square root of x is a slope at any point on that function, and I plug in my x value this time, again, which is 4, and I get 1 over 2 times the square root of 4, which ends up being 1 over 2 times 2, which is just 1/4. So I can find the slope at any point on this graph, and that is really powerful because that gets me one step closer to being able to actually write the equation of the tangent line. And that is what we will be doing next time. Okay, see you in class.